last time we did the linear regression, right? So that should be a no-brainer for you. How many coefficients? A0, A1, right? Well, what's going to happen if we want to improve it? I think we hinted to that last time. Run a higher order. So we'll run a polynomial, all right? So that's what's going to happen as we proceed through these next levels of regression, all right? So least squares can be extended to higher order. How do you do that? You go from linear, quadratic. If I wanted to go beyond this, what would I use? Cubic, right? All right. Sum of the squares of the residuals, right? So if I did linear, I wouldn't have this term, right? So if I want to go quadratic, I just add one more term. All right. Take the derivative of the sum of the squares with respect to the unknown coefficients. I have 3 coefficients. I'm going to have 3 derivatives. What am I going to do with these derivatives? I'm minimizing them, right? So I'm going to set them equal to 0. Can't get any more minimum than that. All right, I can rearrange these equations. Notice all these summations. Why do I have all these sums in there? Because I have a lot of data points. You know, it's not just one pair of points. So I have to do them all. I can rearrange this so it looks like this. All right, now this is important. Pay attention to this because ultimately you'll see there's a real neat trick of solving these things. So you don't have to memorize a lot of this stuff. All right? The important thing, you go from this equation, take the derivative, right? That's what's been done here. I rewrite the 3 equations so they look like this. Now you can see logically what's happening as far as these terms, right? So you can see how they build up. All right, now you have 3 simultaneous linear equations. I would have two simultaneous equations to solve in a linear. So in quadratic, I have 3. All right? Now, if I want to know what's my error, I can find this as far as the standard error. In fact, those are just simple calls you can do in MATLAB or MathCAD or whatever. All right, let's take a look at this and then I'll show you what happens. I have some data that looks like this. If I want to run a linear least squares through that data, I would get a curve or a straight line that would look like that. Now, you know visually by inspection, that's not even close. You know that the trend is this curve shape. Then you realize, and by the way, if you didn't believe that that was, you know, a proper fit, you could also check it by doing what? Remember? The correlation coefficient. It'd probably be a very low number. All right, so I can just bump up the order. All right, in doing so, now I get a fit like this. I go, I would probably buy that one. That looks pretty good. All right, what do we do? Here's an example. Second order polynomial. So I've got x values, I've got y values. I sum all these things. All right, here's the difference. I find the mean. That's what the bar means, remember? So I just find these values. Here's this relation that I can plug in here, squared. So I just sum those values. So here's the data that I have. That actually, once you have the original data, you can set that up to do it almost automatically. Now, here's the trick. See these numbers that are generated? What kind of matrix do I have?
Square.
Yeah, I have a 3 by 3. All right. Do you wonder why I wanted you to learn about matrices? How many unknowns do I have?
3.
How would I solve that?
Kramer's rule.
Kramer's rule, if I do it by hand, or I can use Gauss elimination, no matter what. All right, so I've got it. All right, here's a MATLAB program. Here's the data. All right, I've got N and R, so A equal N over R. A, okay, so I'm just printing out those values. The least squares quadratic equation is blump, blump, blump. That's what I would get. Those are the coefficients. That's all I have to do. I can calculate the standard error. I just plug it into that little equation that I showed you. All right, so I know I have an error. I'm going to deviate on either side of the norm from this by 1.11. All right. Remember what R is?
No correlation.
Correlation coefficient. What would you say? Okay, I take the square root of that. I get 0.99925. I would say it's pretty darn good, right? All right. If I fit the second order polynomial and the data that you saw, so I'd have a least squares parabola. I'd say, yeah, it's pretty darn good, all right. Now, assume that y is a linear function of two or more independent variables. x1, x2, plus, remember the error. Plug it in here, square it. Differentiate. You do this, differentiate with respect to the unknowns, or the coefficients. A0, A1, A2. Now solve three simultaneous linear equations. All right? So there they are. This is kind of the general algorithm or the technique that you would use. Now, if I'm doing this as a quadratic, right, I would have a 3 by 3. If I did this as a linear, what would I have?
2 by 2.
I would have just these terms right there. All right, so once you see how to set the matrix up for a linear, you can easily go to a 3 by 3 or even a 4 by 4. All right. Multiple regression to fit the following data. So I've got x1, x2, and y. All right, substitute into the 3 by 3 matrix right there, and I'll obtain those coefficients. Here's what I get. Here's the 3 by 3. I solve for the unknowns. 5, 4, and minus 3. By the way, here's the equation that I get. How does it agree with the original equation? Perfect. All right, here's what the data would look like now on two variables. So we were dealing with one variable before. Now if we had two variables, you can still do this. It's not difficult. All right, general linear least squares. All right, here's the matrix to be solved. That's a dot, dot, dot. All right, I can carry out as many terms as I want in there. These are the basis functions. All right, z01, x1, z02 is x2, and so forth and so on. You can also use sinusoids. All right, why would we be interested in doing that? I'll show you on a slide shortly. How many of you have had a double E course? Okay.
290.
What do you remember in there? What do you do a lot of? Well, yeah, series, what kinds of series?
Polar imaginary.
Sinusoids. All right. Z is the matrix of the calculated values of the basis functions. These basis functions are these things here. This term, basis functions, that's the same thing that we use in finite elements. So ultimately, when you get into finite elements, you'll say, basis functions, what are they referring to there? That just sounds elegantly mathematical, but it just means that's what these values are setting in here. All right, so now if I want to find, if I take Z transpose Z A, what's that equal to? Z transpose Y. Right? This is why you did those little matrix manipulations at the beginning of the course. All right, so repeat the previous example using polynomial regression with MATLAB. Here's X data, here's Y data, Z. You call ones size X, X squared. All right, here's the table data. All right, so that's a transpose or a prime. All right, here's the answer, here's the coefficient that we got, and then the answer that you get.
What is ones? I've never heard of that command before.
Yeah, it's just, it depends on what version of MATLAB do you guys have? All right, is it, what, do you have any toolboxes with it? Is it the student version or just a normal version? I tell you what I'll do. I'll take the code that I did for the homework and I'll put it on there, but there may be a couple of calls in there that I use that you may not have. Usually I get the full-blown version and that's all kinds of things. But I think you guys should be able to do that. All right, repeat the previous example using polyfit function in MATLAB. All right, here's the polyfit. A equal polyfit, x, y, and 2. Here it is, boom, it just throws out the answer right away. All right, so pretty simple. All right, now nonlinear regression. All right, now I put some calls in here. Fmin search provides an optimization routine that you can determine values, obviously, for A0 and A1. Right, that's the general syntax. Actually, you can look this up. I'm not sure if it has MATLAB descriptions of functions in the back of your textbook. You might want to take a look. If not, I think you can probably go online and track a lot of that stuff. All right, so these are just some of the arguments that you put into this thing. So here, use on linear regression to find the following data. Use initial guesses of 1 for the coefficients. All right, plug it in. Here's the function call. Right, sum, fmin search.
What's the cat symbol? I've never seen that when you use the MATLAB code either.
Yeah.
What is it for? Just it's looking inside that function?
Yeah.
Another info?
That's what you're doing. There's a lot of things that are built in as far as kernels. They call them kernels, K-E-R-N-A-L. Kernels in MATLAB. And that's why sometimes you're treating this thing as a black box. And you're trusting whatever comes out of it. And you may be wrong. It may be that the kernel is correct, but you either have loaded it wrong or it's not being used properly.
The 2.5384 and the 1.4359 is what goes in that bracket between the 1, 1, and
That's
X, Y?
well, that's the answers that come out.
Is that
as far as
X
the
and
goal.
Y, or is that what's supposed to be in the bracket in between them?
Oh, here?
X1 matrix of the mode.
Yeah, that's here.
Okay. So it's
Okay.
what's supposed to be in those brackets?
Anyway, here's what happens. If you transform, you wind up getting this curve that goes through the data like so. If you don't, then you get something that fits like this, which may not be quite as good. All right, that's all. That's what's going on. So it's doing some juggling for you. All right, now this is why I was saying, why do we go to sinusoids and so forth? How many of you have used Fourier transforms? Why? What you do with Fourier transforms? Signal analysis, right? Electrical engineering, all sorts of stuff. All right, for a function with a period t, you can do a continuous Fourier series that generally you write like this. That goes well, as far as you go. Depends on how many terms you want to carry. Or you could rewrite it in terms of this, summation k equal 1 to infinity. Right? Okay. Here's the fundamental frequency, 2 pi over t. Here are the multiples. These are the harmonics that you deal with. That's what you're, the little omegas that you see. All right, so you can find what you're after are the coefficients. So A and B. I remember having to do these things by hand, especially when I was doing quizzes. Yeah, not fun. All right, use a continuous Fourier series to approximate a square wave. So here are the conditions for the square wave. All right, average height of the wave is 0, a value of A, 0 equals 0 can be obtained directly. All right, here are the other coefficients. So this is what you're solving for. You evaluate the integrals. These are 0. Here's what you get for the A's. All right, now let's see what happens. Fourier series approximation now looks like this. All right, so here's the square wave, right? This is what we had. What we're trying to do is to approximate that as accurately as we can. All right, so if we just look at this term, this is what we get. If we add that term, all right, what's happened? Yeah, we're adding more harmonics, right? If I add now another term, how does it look? You can see that what we're doing by adding more terms, we're getting closer and closer to the true shape of the square wave. What's this remind you of as far as what we're doing here? Taylor series, right? All right, now, there's a nice little table that's in your book with regards to the summary of the methods. And this is kind of a good one to refer back to. Linear regression, all right, remember this one, the polynomial. We can account for curvature. How do we do that? Just going to a higher order, to a quadratic. Multiple regression if I have more than one variable, like an x1, x2, or whatever. Newton's divided difference. You remember this? Remember when you did this? Interpolation. What I did was introduce the interpolation to you early, but it's really rolled into curve fitting, Right? That's why we bounced around. So at the beginning, so that when you came to problems like this, you could go, oh, I already know how to do the interpolation if I wanted to do that. But maybe I don't want to put a curve through all the points. I want to look at some trend. You know, what is the data telling me? All right, so finish up the chapter on curve fitting. Take a look at Fourier approximation. For those of you that haven't used it, guess what? You will. You will have to use it in some of your courses coming down the road, particularly if you haven't had a double E course. All right, now next week we're going to talk statistics and probability. I've got 2 guest lecturers coming. The first fellow is Angelo E. Fontes. How many of you know who Angelo is? Right? I think I mentioned him once before. He's a professor in computer science. His expertise is really in visualization, but also statistics. And he wrote the gaming code for Nevada Gaming, for like the slot machines and other things.
Oh, you can give some tips.
Do what?
You can give some tips.
You know what he'll probably tell you? Don't gamble. Plus the fact that nobody can break my code. I just love a challenge like that. So anyway, he will talk about statistics and probability. He does a lot of very interesting things on the outside, including UAVs, compression algorithms. How do you take miniaturized cameras, compress the image? And he's done it, I think, upwards of 500 to 1. Nobody has come close anywhere.
Did you say UAVs?
UAVs. Yeah, he's also an avid pilot. So, now the other fellow, also a professor in computer science, is Laxmi Gowala. All right, his expertise is in programming languages. Anything you want to know about programming, regardless of what it is, he's the guy that you go to. He's also an expert in computational geometry. Now you're going to find how important that is when we ultimately get to PDEs, because we'll be setting up simple meshes. We have to discretize or create a mesh of a problem domain. And so he's really the expert in that. He was also the chair of the teams that we had used some years ago in national competitions, where the UNLV team, where you're given a problem and you have to go program it and solve it. And I think we were #2 twice in the nation. So he was the advisor for that group. You know who we lost out to? Caltech. So if you got to lose to somebody, hey, Caltech's okay. But that means we beat everybody else, including MIT and those schools underneath. That's how good he is. I've used him in the past. He and I have done some Java coding, the adaptation, all sorts of stuff in there that you go onto the web and boy, you get an instant solution. He's one of the best there is. All right, so these are guest lectures that will be coming next week. So Angelo on Tuesday and Laxmi on Thursday. All right, any questions? All right, see you next week.